Hi, welcome back to Moose Chemistry. This is electron configuration of Niobium. Niobium is element number 41 on the periodic table. So it's going to have 41 protons. Since it's electrically neutral, we'll have 41 electrons. Its AMU mass of Niobium is 93. That's the number of protons and neutrons. So how many neutrons do we actually have? Well, remember, you go AMU, the number of that, minus the protons equals the number of neutrons, right? So you would go 93 minus 41 would equal, of course, 52 neutrons. All right, so let's go ahead and put 52 right there. Now we determine the number of neutrons. Let's remember something here, that the S can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell can hold 14 electrons. Now we're going to use the off-ball principle, which clearly states that you have to fill the lower energy levels first before filling the upper energy levels. And we're going to use something called the diagonal rule, and we're going to start right here on these slides, these arrows, and continue to fill all these subshells until we run out of electrons, which would be 41 of them. So let's go ahead and do that. So we want S2, there you go, there's 2 electrons used up. And then we go to this one here, 2s2. All right, then we go to this slide here, 2p6, 3s2. We go to this slide here, 3p6. Then we go 4s2. Pretty darn easy, huh? Then we go to this slide here, 3d10, 4p6. Now remember that Niobium is an exception, so we're just going to go 5s1. Go to the next slide, and we go 4d4. Again, normally you would say something like 5s2, 4d3, but Niobium is an exception, so we can't do that. We have to call it 5s1, 4d4. Okay, orbital notation, that deals with Hund's rule. Hund's rule says that you have to put an up arrow in every suborbit of that orbit before you can put the down arrow. So watch what we do here. So the up arrow is the clockwise electron, and the down arrow is the counterclockwise electron. So up and down. Here's a classic Hund's rules. Look at this. 2px, 2py, 2pz, right? Up, 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 and then down, down, down. That's Hund's rule at its best. So let's go ahead and fill in the other ones. See how easy that is? So 4px, 4py, 4pz. Up arrows for every suborbit, now the down arrows. See that? Hund's rule. Here's our exception with our 5s1, and then now here we come with the last 4 electrons. Do we need to have that 4dz square in there? Yes, you do, because remember that electrons can jump at suborbits and even orbital levels. Okay, let's look at our noble gas notation. So what's the nearest noble gas to Niobium? It's krypton. So we're going to put Kr in there. And krypton takes up everything. Everything. Its electron configuration ends in 4p6, right? So that's going to give us 4d4, 5s1. Now, let's look at Pauli's exclusionary principle. That's the quantum number notation. Pauli's exclusionary principle says that no 2 elements can have the same set of quantum numbers, right? Now, remember that Niobium, although it looks like it's in period 5, let's remember the D block is n minus 1. So you would go 5 minus 1 will give us 4 for our principal quantum number. Since it's in the D block, it does have an L value of 2. And because it's an exception, it's not going to be 0, it's going to be 1. So we're going to put a 1 there. And our last error right there is going up, so that makes it 1/2 positive. Pretty darn snarly, eh? So, that's about it with this one. So, if you like this video, give us a like and consider subscribing so we can grow this channel. You guys be snarly, and we'll see you back here at Musin Chemistry!